The topic of this video is producer theory. Whereas the goal of consumer theory was to derive the consumer's demand function for a good, producer theory has the goal of deriving the supply function for a good. To determine the supply function for a firm, we have to proceed in two steps. First, we are going to look at production technology, which is the subject of this video. And second, and that will be the subject of the next video, we are going to look at cost theory, which is based on producer theory. It is the combination of producer and cost theory that allows us to derive the supply function of the firm. Now, let us have a look at the graph in front of us. For producer theory, we assume that we have a firm that is converting one or more inputs into one output using production technology. We will soon see that those inputs can be either fixed or variable. Think about a carpenter who is going to take the input wood and convert it into the output chair through their ability as a carpenter. Throughout this section, we only look at the production of one type of good. Now, in reality, it is difficult to observe the production technology of a firm directly. In the section on cost theory, we are going to see that if we have knowledge about the quantity of outputs and the total cost associated with that output, we can say something about the production technology through a concept that is called duality in economics. In producer theory, we are going to represent the production technology with the help of what is called a production function. Now, I would like you to think about a production function very broadly. So above, I was talking about production technology where we had wood being converted into chairs using a production technology. Now, think about this a little bit more broadly. And let me do two examples. And that will also introduce the your first production function. Now, think about any college class that you're going to take, and you have the input time. Okay? So that would be your one input. And the output is the grade. Okay? Now, let's assume that the more time you spend on a class, the higher your grade. Okay, so here we have time as the input, and the grade would be the output. And think about your ability as the production technology. Now, if you're spending 0 time on a particular class, then your grade is going to be accordingly. Okay? Then assume here that you're going to get the lowest grade. Say, let's make this an F. Okay? But usually in many classes, that if you start to spend a little bit of time for a class, that your grade is going to increase significantly. Okay? And that the more and more time you're spending on a class, then your grade is still going to increase, but at a much lower rate. Okay. Note that we have seen something similar in consumer theory, where we called it decreasing marginal utility, whereas here in this concept or in this producer theory, we're going to talk about decreasing marginal productivity. Okay. So here you would have your production function that exhibits decreasing marginal productivity. The more time you spend, then you may be able to get, depending on your ability, you may be able to get to the grade of A. Okay. But it's going to be usually more and more difficult. So this is one example. Now think about the other example that is going to be slightly different. Okay. Now think about running 100 meters. Okay. So the current world record is at 9.58 seconds. Okay. Now suppose that you want to improve your time to run 100 meters. Okay. So here is the input would be the training time. And basically output would be the improvement of your current time. Okay. Now suppose that we have the 9.58 seconds here, which is the current world record. And suppose that if you are untrained, suppose that it takes you, say, 15 seconds to run 100 meters. Now, if you're going to start training, then you're going to improve initially, and you're going to approach this world record. But no matter how hard you train, you are not going to reach this world record. Okay, but you're going to exhibit this decreasing marginal productivity in the sense that a little bit of training is going to increase, or it's going to improve your 100-meter time, but it gets more and more difficult. Okay, which is another example of this decreasing marginal productivity. Now, let us move to a more economics application. What you see here on the left-hand side is the production technology of a farmer or of a field. You have the input fertilizer and you have the output yield. The yield is how many bushels of corn you can harvest from an acre, for example. Now note that, of course, this is not quite correct since I have started at 0 in the sense that if you apply 0 fertilizer, you get a yield of 0. Okay, but this is only for, in reality, this is not true. Even if you do not apply fertilizer, you are going to have a yield. But in order to make it compatible with the economic theory, let us assume that it starts indeed at the 0. So what this production function says that if you're going to apply fertilizer to the field, okay, then you're going to see your yield increasing, okay, but it is going to increase at a decreasing rate, okay, in the sense that you're going to get into a region of fertilizer application where you're only going to have very little additional yield, okay, because you're basically reaching the biological limit or of the field. Note that if you apply, say 100 pounds of fertilizer per acre, then what the production function says is that with the 100 pounds of fertilizer per acre, you should be able to get about 160 bushels of corn. Okay. Note that given this production function, it is not possible that you can achieve more than 160 bushel of corn with an application rate of 100 pounds. Okay? In the sense that this upper region here above the production function is not attainable. Okay? Now, of course, everything below the production function, everything here is attainable, but it is not efficient. Okay, so if you are using 100 pounds of fertilizer per acre, and then you only get, say, 50 pounds of yield, then this has not been an efficient application. Okay. Now, in order to determine or in order to explain the efficient and inefficient points, let us consider the graph on the right-hand side. Okay. Now, Suppose that you are using 100 pounds of fertilizer, okay? Then you can achieve the point of the output of say 100 bushel, okay? But this point would be inefficient, okay? Whereas with 100 pounds of fertilizer, you can only achieve, say, 160 bushels of corn, and the point of 200 pounds is not attainable. Okay, we have seen this in the past. So let me illustrate what we have just seen about the efficient and inefficient points. And for this, I will come back to the example where you're producing a grade in a college class. And so the grade is your output and your input is time. Okay. Again, this is the input and the grade is the output. Now, suppose that based on your ability that you have a production function that looks like this, and that you are, say, spending, let's say you are spending 3 hours on a class. And given that you are spending 3 hours on a class, that given your production function of converting time into grade, you should be able to get a B. Now, suppose that you are listening to music while you are spending time studying for a class, okay? And suppose that the music distracts you, then despite the fact that you are spending 3 hours on studying for a class, that you only get a C, okay? Now then again, this point is inefficient. And you can see that by looking at this from two angles, if you will. Either you turn off the music and you're still spending 3 hours and you're moving from a C to a B. Okay. So that is one possibility. Or again, you turn off the music and you just say spend 1.5 hours on studying. And if you're spending 1.5 hours, then you're getting the C. Okay, so there are two ways of moving from the inefficient point to the production technology, or to the production function. Okay, so again, here you are spending 3 hours, you turn off the music and you're getting a B, or you are turning off the music, you're spending 1.5 hours if you're happy with the C, and that is also efficient. Now, in producer theory, we are going to differentiate between production in the short run and production in the long run. Production in the short run means that one or more inputs are fixed and cannot be adjusted. Suppose that you have a shoe store and you are selling shoes in a rented store. Now, the store size is fixed over 1 year. If, for example, you have signed a rent or a lease for 1 year, and even if you want to expand or you want to contract the size of your shoe store, you cannot do so because you are locked into this space for 1 year. Okay. Now, in the long run, all inputs are flexible in the sense that, coming back to the example of the shoe store, that if you want to adjust your output or your ability to sell shoes, and you want to go either into a smaller store or into a larger store, then you can do so in the long run, but not in the short run. Now, for the purpose of this class, and also for producer theory in general, we can differentiate two inputs. We have capital, which is denoted with the letter K, and we have labor, which is denoted with the letter L. Now, usually we assume that capital is fixed in the short run. So think about machinery, or think about the size of a shoe store. And you can only adjust labor in the short run. Okay, so labor is flexible. So note that capital, again, is fixed in the short run. And to denote that it is fixed in the short run, I put a little bar over here. Okay, but usually the bar is not necessary. Now, in the first step, we are going to look at production in a short run, in the sense that we assume that one input is fixed, and we are only going to look at labor. When we look at the production function in the short run, okay, then the advantage is that I can actually represent it in a two-dimensional graph. In the sense that we have the input, let's say that this is labor, okay, that's labor in the short run, and that we have the output, okay. Now note that you can think about capital and labor as placeholders. There are, of course, many inputs that are either fixed or flexible, okay, and historically the capital and labor have been used as to denote or to represent those inputs. Now here I have drawn a production function, and note that the production function is slightly different from what we have seen before, in the sense that it is not bowed through the entire range of inputs, but we actually have increasing returns, what are called increasing returns to scale at the beginning, okay, for low inputs, and then we have decreasing returns to scale up here. Okay. Now, what this means is the following. In this part, if you are increasing your labor, then you have a more than proportional increase in your output. Whereas for decreasing returns to scale, you have less than proportional increase in outputs. Okay, and we will see that we are going to use this particular shape for to explain the concept of marginal product, or what is called marginal product and average product. This shape actually makes what I'm about to present more easier. Now, let us introduce two concepts that are called marginal product and average product. Now, marginal product, or marginal product of labor, let's call it MPL, okay, is defined as the change in the production quantity, or the change in output, over the change in labor. Okay, so the little delta here, that means change in. Okay, and think about the marginal product of labor as the slope or the steepness of the production function. Okay, so think about you are walking up this production function, then the marginal product of labor is very low here. Then here it is much steeper, so the marginal product of labor is high. And up here, the marginal product of labor is low again. Now, we also have a related concept, which is called the average product, or let's call it the average product of labor. And the average product of labor is simply the total quantity of output divided by the total number of workers. So, for example, if you are producing 100 chairs, okay, and you have 4 carpenters hired, then the average product would be 25 chairs per carpenter. Okay. Now, let us represent the concept of marginal product and average product in this graph here. Okay. And let me start with the concept of marginal product, because it is slightly easier to explain than the average product of labor. So I'm going to use the green color to describe the marginal product of labor. Now, I mentioned before that the marginal product of labor, or the marginal product, is the slope of the production function. Okay? So we said before that about at this point here, that the slope is steepest. Okay? And there is no other point on the production function where the slope is steeper than here. Okay, so here the marginal product to the right is lower than at this point, and the marginal product to the left is lower than at this point here. Okay, so what this means is at this point the marginal product of labor is highest. So let us represent this up here. Okay. And so, since the marginal product of labor is maximized at this point, it is lower everywhere else, and hence the marginal product of labor looks like this. Okay? So this is the marginal product of labor. Okay? Think about this graph representing the slope of this line. Okay? We said that marginal product of labor is very small here and very small here. This is represented by the fact that the marginal product of labor down here is very low, whereas the marginal product of labor is very high, or it's maximized here, and hence we have the maximum product or the maximum slope at this point. Now, we can also represent the average product of labor in this graph. And for the average product of labor, I am going to use the red color. Okay. So it turns out that the average product of labor graphically can be represented as follows. Let us take this particular point here, okay, where the marginal product of labor is maximized, and let us connect this point to the origin, like this. Note that what you have now, so if you have this point connected to the origin, then what you have is that you have Q here, the output associated with this point, and you also have L here, okay, which is the labor, the number of workers associated with this point. The average product of labor is Q over L. So you have Q over L, you have rise over run, and hence what this means is that the slope of this connecting line represents the average product of labor. Now, the question is, how do we represent this slope in the graph below? Now, remember that the steepness of the production function, let's look at this slope here, that this steepness, okay, is represented by the marginal product. Now, the question is, well, what is steeper? This green line here, which represents the slope, or this slope here? You can see that the green line is steeper, and hence what this means is that the red line, or the average product of labor, at this point has to be below the marginal product of labor. Okay? Now, let us look at a different point. Specifically, let us look at this point here. Okay? Now, in order to determine the average product of labor at this point, we have to connect this point to the origin, like this. And then the slope of this connecting line represents the average product of labor. Now note that for this particular point, the slope of the production function is identical. So what this means is that at this point here, the average product of labor and the marginal product of labor are identical. Okay, so hence the average product of labor is here. Now what you will see is that there is no other point on this production function, okay, which you can connect to the origin and that gives you a steeper slope. What this means is at this point here, the average product of labor is maximized. So APL is maximized. Okay, and it is lower at any other point. So this point here represents a maximum of the average product of labor. So what this means is that we have this inverted U-shaped curve with this point being at the maximum. Okay? And this red line here represents the average product of labor. Note that in none of what we have talked so far, when we talked about production technology, production functions, short run versus long run, that we have included input prices or output prices. Okay? We will see that this concept of marginal product and average product is going to be very important when we are going to look at the cost theory in order to derive the supply function of a firm. Before we move to production in the long run, let me illustrate the derivation of average product and marginal product on this graph, which has been generated with a computer. Now let us first look at the marginal product. The marginal product, again, is the slope of the production function. And we can see here that the marginal product is maximized at this point. And this represents the point where we are moving from increasing returns to scale to decreasing returns to scale. Okay? So the steepest slope of the production function is right here, and that is indicated by the marginal product being maximized. Now, the average product, to get the average product graphically, you have to pick a point, the point you're interested in. You have to connect that point to the origin, and then the slope of this line represents the average product. And as you can see here, the slope of the red line is less than the slope of the production function. And hence, the average product is below the marginal product at that point. Because here, you have the average product. Okay? And note that at this point here, let me mark this in the graph. This is the point where, if you connect it to the origin, that the slope of the connecting line is the same as the slope of the production function. And hence, at this point, marginal product and average product are the same. Now, let us look at production in the long run. Remember that production in the long run is characterized by the fact that both inputs, capital and labor, or any other inputs, are flexible, in the sense that you can adjust them as you want. Now, before we start, let us have a look at this production function here. Now here, this is something similar what you have seen already in consumer theory, okay, where we have on the left-hand side, we have this three-dimensional representation of a production function. And so you can assume that on one axis or on the x-axis, you would have labor. On the y-axis, you would have capital. And the z-axis, or the height, that would be your output. Okay? And think about this as a three-dimensional shape. And so when you are looking from above on this production function, then you can see that you have those contour lines. Now, here on the right-hand side, we have the same information presented than on the left-hand side, but here we are looking at the production function from above, where we have, here I called it X and Y, but here that would be labor and capital on the y-axis. And then the height would be the output. So for example, if you take the contour line right here, this would produce an output of 8 units of whatever you are producing. And here you have all the combinations of labor and capital that would produce you 8 units. In consumer theory, this was called an indifference curve, whereas in production theory, we will see that we call this an isoquant. Iso means same quantity. So all the combination of capital and labor which are on this isoquant produce you the same quantity of output. With production in the long run, all inputs are flexible. And here I have represented what we have just seen, in the sense that we have the inputs on the axis, capital and labor, and we have isoquants that are indicating of what are the combinations of capital and labor that produce the same units of output. Here I have drawn two representative isoquants, one for the output of 10 and one for the output of 20. So note that, and this is on a side note, that usually you have labor on the horizontal axis and you have capital on the vertical axis. Sometimes myself, I get confused of what is on the vertical axis and what is on the horizontal axis. And so how I remember it is that there is a Dutch airline company called KLM, so KL, and this is how I remember of what is, in which order it is on the axis, okay? Now note that we said that we have the isoquants, so here we have one particular isoquant, which indicates all the combinations that produce this 20 units of output. Note that if we have a particular point here, okay, let's call this L1 and K1, okay, so this is some combination of labor and capital to produce 10 units. Then if we want to increase labor, but we want to produce the same number of units, then we have to decrease capital, okay? And then we remain on the same isoquant. Now, the ratio at which we have to replace one input for the other to remain on the same isoquant is called the marginal rate of technical substitution. or MRTS. Okay, and again, this is the marginal rate of technical substitution. Actually, there is TION. Marginal rate of technical substitution. Note that the MRTS represents the slope at a particular point. So here, it represents the slope of the isoquant at a particular point. So the slope that is tangent at a particular point, the slope here represents this MRTS. Now note that in everything we have done so far, when we talked about production functions, average product, marginal product, production in the short run, production in the long run, is that there has been one important aspect that we haven't talked about yet, and that is cost. Now, every firm wants to minimize its cost to produce something, okay? And so let us start considering cost. So the input K and L are, if a firm uses them, are of course not free. And so the price of capital is usually considered the interest rate, okay? And we denote that with small r. And the price of labor we denote the price of labor with W for wage. Okay? So based on this notation, we know that the total cost of the firm is written as the price of capital R times K plus wage, the wage per worker, times L. Okay? So this represents the total cost of the firm. Now note that we can rewrite this, and keeping in mind that this is very similar to what you would have seen in consumer theory about the budget constraint. But here the difference is that for the firms, the firm can choose the level of K and L, and it is not bound to a particular total cost. So in the portion of consumer theory, we had a consumer that has an income, and the income cannot be exceeded by the amount spent on various goods. Here, in this case, there are no restrictions on K and L in how high they can be. Okay, we will see that we can determine what is the optimal combination of K and L. Okay, but the total cost is not restricted. We can rewrite this total cost as follows. We can make this a function of K, function of capital, and note that the capital is what you have on the vertical axis here. We can rewrite this as the total cost divided by R minus W over R times L. Now here you have an intercept, and the entire part here, the negative W over R, and please keep in mind that this is the ratio of the input prices, or ratio of input prices, that this represents the slope. Okay. here we have now all the components that we have talked about before. So we have the total cost, which is the rental rate of capital times the units of capital plus the wage per worker times the number of workers. And we can reorganize this term by writing it as a function of k. And so we have an intercept and also a slope term. Now this is very similar to the budget constraint, but we do not have a budget constraint for a firm, but we have what is called an isocost line. Iso again means the same cost, in the sense that all the combinations of capital and labor which are on this line have the same total cost. And note the slope of the isocost line is the ratio of the input prices. Now we also have the isoquant line, which I represented here for 10 units of output. Okay. And the slope of the isoquant line is the marginal rate of technical substitution, or MRTS. Now, the question is, well, how does a firm, based on input prices and based on its technology, which is in part represented by this isoquant here, how does a firm choose the right combination of capital and labor or any other inputs to minimize their cost? Now, consider this point K prime and L prime, which I have marked in this graph. The question is this point, this combination of capital and labor, efficient or cost minimizing to produce 10 units of output? And the answer is no. Why is that? Now consider a slightly different combination of capital and labor. Say here, say in this case, so this should be a tangent. Okay. Now if the firm chooses L prime and K prime, L star and K star instead of L prime and K prime, then it produces the same amount of output, 10 units, but it does so at a lower cost. Now, why is it a lower cost? Now, consider this point here. Okay. Note that this point has also the intercept of total cost divided by R. But note that here, since R is the same in both cases, but here we have a lower intercept, this means that the TC here, this one here, has to be lower than the total cost associated with this input combination, or this combination of input. And hence, the total cost in this case is minimized if the firm is producing at L star and K star, as opposed to L prime and K prime. Now, what are the characteristics of this particular point here? You will see that since the slope of the isocost is the ratio of the input prices, so we have the ratio of input prices, and since it is tangent, it means that it is also, the slope is equivalent to the marginal rate of technical substitution of the isoquant, and hence the optimal combination of inputs for the firm is where the marginal rate of technical substitution is equal to the ratio of the input prices. Let us do an example to see how this model works. Suppose that we have an electric utility which produces electricity from a combination of natural gas and coal. We have the price of natural gas, Pn, and we have the price of coal, Pc, and N and C represent the physical units of natural gas and coal. As we have seen before, we can rewrite this as a function of N, since we have N on the vertical axis. And so we have the total cost divided by the price of natural gas minus the price of coal over the price of N times C. This equation here describes the isocost, which is represented in this graph. Note that I have also drawn an isoquant, which is tangent at this point here, which I labeled C1 and N1. So given the price of natural gas and the current price of coal, then this is the optimal input mix to produce electricity. Now, note that we now have a scenario where we say that we have an increase in the price of coal. When we have an increase in the price of coal, that means that Pc is going to increase, it's going to go up. Now, when the price of coal increases, then you should notice that the slope here, which is price of coal over price of N, or the negative of the price of coal over the price of N, is not going to be the same anymore. Okay? But since Pc is increasing, the slope is going to get steeper, like this. So if the slope gets steeper, this initial point here is not optimal anymore. So now, when we assume that the firm can actually choose the quantity of natural gas and coal, then if the slope gets steeper, then we are now in the situation where we have a new tangent here, okay, which now represents the new combination of natural gas and coal to produce electricity. Now, as you can see, the model predicts a decrease in the price of, predicts a decrease in the usage of coal and an increase in the price of natural gas. So we now produce electricity using N2 units of natural gas and C2 units of coal. Intuitively, the model is correct because the price of coal is increasing, so it gets relatively more expensive compared to natural gas. And hence, we are moving away from coal and using more natural gas. So the model which we have developed in this section correctly predicts what happens when we have a change in the input prices. The last topic we are going to talk about is the short run and long run expansion path. Note that a lot is going on in this plot, and I am going to explain the various parts step by step. Now, let us consider that we have capital and labor, and let's assume that capital is fixed at this level in the short run. Fixed means that no matter what the output decision is of the firm has to use K bar units of capital. They cannot change that in the short run. Now, suppose that initially the firm produces on this isoquant, let's call this IQR, IQ1, okay? So that is the isoquant the firm is currently producing at, and they're using the K bar, and let's call it L1 units of labor. Okay, so they are at this point. You have the isoquant, you have the isocost and their tangent at this point. Now suppose that for whatever reason the firm has to increase output. So you have IQ2 and IQ3. Those are isoquants that are associated with more output. Now, since the firm is fixed at K bar, if they want to produce more units of output, then they are moving along this line, which is called the short-run expansion path. Why is that the case? Well, K bar is fixed, so they always have to use K bar units of capital. Now, the K bar units of capital and L1 units of capital may have been efficient for the lowest output here, the say IQ1, okay, that is say associated with 10 units of output, but it may not be efficient for higher levels of output. Okay, so assume that actually instead of 1, 2, and 3, let's call it 10 units, 20, and 30 units. Okay, make it easier. So if the firm now wants to produce 20 units of output, then they have to use this combination of capital and labor, but this may not be efficient in the sense that it is not cost minimizing. And you can see that the isoquant is not tangent to the isocost line at this point. Now, why is the firm producing at this point anyway? Well, because capital is fixed. So the red isocost line here is the cost or is the isocost line associated with the situation where the firm is in the short run and cannot adjust all the inputs accordingly. Only in the long run, when actually the firm can move away from K bar units of capital, they can adjust their input using fewer units of labor and more units of capital to arrive at this point here. Okay, so if they have to produce 20 units of output, then they want optimally, or in a cost minimizing sense, they would like to produce at this point here with a combination of say L2 units of capital, L2 units of labor, and K2 units of capital. Okay. Now the same is true if they have to move say to 30 units of output. Then again, if they are in the short run and they are fixed at K bar, they have to produce at this point, which is not cost minimizing because the isocost line is not tangent to the isoquant line at this point. But since capital is fixed, they do not have a choice. Now, only in the long run, when they can adjust all the outputs freely, can they move to this point here. Let's call this L3 and K3, where this point here is cost minimizing. Now, if you have the short run expansion path, this is associated with the fixed unit of output, with the fixed unit of K bar. You also have a long run expansion path, which connects all the points of capital and labor that for a given price level of input prices where the firm is going to produce. Okay, it connects the points of the optimal units of capital and labor that given input prices produce the output units.